Okay, so in this video, this is the first video in the Algebra 2 series, and we're going to be covering chapter 1.1, Language of Algebra. And so we're going to be talking about a lot of the things that you need to just kind of get through before you can really start doing the new Algebra 2 things. A lot of these things are going to be reviewed from Algebra 1, but it's always good to go back through and try them again and just revisit these topics. So the first thing we're going to talk about is the idea of factors and products. So factors and products have this relationship where factors multiply to form the products, right? So you have 2 and 3, for example, and you multiply them and you get 6. And so in this situation, then we have these guys right over here. Those are the factors. And then this guy, the 6, that's our product, right? So very simple concept. You're probably familiar with this even just from elementary school. And so what we can do with this is we can take a specific product and we can break it down into different factors. So for example, if we take 24 is an example, and we want to, that's our product, right? And we want to break this down into factors. Well, we could say, okay, well, 24 is 2 times 4 times 3, right? These are all our factors right here. And then this is our product, right? So if we take our 2 times 4 times 3, you might notice that this 4 here can actually be turned into more factors than just the factor itself, right? You can say that's actually equal to 2 times 2 times 2 times 3, right? That's, here, let's fix that too. 2 times 2 times 3, right? Because 2 times 2 is 4. And so what's interesting is that sometimes we can reduce these, right? We can turn a 4 into a 2 times 2 or 6 into a 2 times 3. Sometimes we can do that. Sometimes we can't with certain numbers. So for example, these 2's and 3's that we have here, there's not a whole lot we can do with that, right? Because 2, well, what's 2 divisible by? Well, you could multiply it by 1, and you can multiply it by 2. What I mean by that is 2 is not, the only factors you could split 2 into, if we wanted to factor 2, is 2 times 1, right? That's all we could do. And that's pretty useless here. So what we actually, when we get a number down to this state where it can not be factored any further, we call this, so let me just kind of clean this up a little bit. So 2 times 2 times 2 times 3. This right here is what we call the prime factorization. And the reason we call it the prime factorization is because we have taken this number and we've broken it down into the prime numbers that make it up. And so in order to kind of understand that more, we'll briefly cover what a prime number is. So, and I just kind of explained it just now. A prime number, so let's go here. A prime number is basically any number such that you can't break it down any further, right? And technically what we'd say is that a prime number is when it's only divisible by 1 and itself, right? So in our example with 2, 2 is only divisible by 2 and 1, right? There's no 3, there's no 4. And of course, we're only talking about whole numbers. So like, yes, you could divide 2 into like 0.5, right, times 4. But we're talking about specifically whole numbers in this case. With a prime number, you can't break it down into anything other than just itself and 1. And so these turn out to be really useful, and we'll get to that in a second. But when we get to a prime factorization, all that means is that all the factors in that factorization are prime numbers. So let's take another example, just off the top of our heads. Let's do 32. Okay, so we are going to find the prime factorization of 32 here. And we're just going to start by breaking this down. So what's 32, just off the top of your head? Well, we know it's 16 times 2, right? Now notice 2 is a prime, right? We can't break 2 down any further, but 16 is not. Why? Because it's divisible by 2, by 4. It's divisible by a number of things. We can break it down further, so let's do that. 16 is actually equal to 4 times 4, right? And then we still have that times 2 here. Those 4s can now further be broken down. And so here we have, okay, that 4 is 2 times 2 times, okay, this 4 is also 2 times 2. And then our last 2 at the end there, right? So I'm just going to kind of mark these so you can kind of see where everything is going. Right, and then that's our last 2 at the end. So you can see we've just kind of split this 4 into a 2 by 2, this 4 into a 2 by 2, and that 2 just stayed the same. And so now you'll notice we've come to the point where all of these numbers are prime numbers, and they all happen to be 2. And so, again, this is our prime factorization. And so what we can do with this is kind of like the most reduced state of the number, right? It's like we've found what all the ingredients are. And so we can now build this number back up by multiplying them all together, or we can do some other useful things. So for example, one thing prime numbers are really useful for are for finding the roots of numbers. So for example, let's say, well, actually, let's just take 32. Let's say we wanted to find the, let's see, let's do the 5th root, right? You might see where I'm going with this, of 32. Well, what we can do is we can break it down into its prime factorization, and once we have it down into its prime factorization, we just look for prime factors that repeat in sets of 5, right? So if we come here, we can say, okay, this is the same as the 5th root of, and we already did that prime factorization up here. So we can just say it's the 5th root of 2 times 2 times 2 times 2 times 2, right? And so now we can see, oh, well, this 2 times 2 times 2 times 2 times 2 repeats 5 times. We can actually evaluate that 5th root now because we know we take this repeating section that repeats 5 times, and we just pull that out as 1. And so we're evaluating the 5th root because we can see 2 was multiplied by itself 5 times to get 32. So the 5th root of 32 is 2. Don't worry too much about that. That's not really an Algebra 2 specific thing we need to worry about. That's just an example of where prime factorization is useful. A more important example is actually the next topic here, which is the least common multiple. And so what this idea is let's say we have two numbers, for example, 12 and 18. So we have these two numbers here. And we want to find the least common multiple. And so what the least common multiple is, and I'm gonna put a lot of these definitions. I'm gonna try and put them as words on the screen here. It's gonna be the smallest number that's divisible by both of those two numbers. It's gonna help probably more just to have an example because that's not a very intuitive thing to say. So let's just kind of have an example with these two numbers, 12 and 18 here. So if we take 12, and we want to find the least common multiple of 12 with 18, what we'd start by doing is looking at the prime factorization of these two numbers. So 12, let's break it down into its prime factorization. That'll be 4 times 3, right? That's our preliminary factorization. We know 12 is 4 times 3, and what is 4? Well, 4 is 2 times 2, and then we still have that times 3 hanging on there. So this is the prime factorization of 12 right here. And now let's do it with 18 as well. 18 is 3 times 6, and so we can still split that 6 up into a 3 and a 2, right? So we have now 3 times 3 times 2. So that is the prime factorization of 18. So now that we know the prime factorizations of these different numbers, what we can do to find the least common multiple, the least common multiple is going to be the number, the smallest number, where you can take either of these prime factorizations out of it, right? It contains both of these, and that just means that it'll be divisible, and I'll show you what that means. So in this case, let's say let's just start by putting in, so we're going to build the LCM here. We're just going to put in the prime factorization for 12 right now. 2 times 2 times 3. And then we're also going to need to have everything we need for the 18 prime factorization. And so what's interesting, we already have 1, 3, right? That's over here. We already have 1, 3. And we already have the 2 covered. See, this 2 and that 3. So we just need to add another 3, right? And so now you can see, and I'm actually going to rearrange this just a little bit to be, I'm just going to kind of turn it around actually. So this is going to be the same thing as 3 times 3 times 2 times 2. This is the prime factorization of the least common multiple. And what's interesting is that you can actually see both of these prime factorizations of these other numbers in this number. So I'm just going to make the 12 be colored blue. Just that's a blue box, right? And then we're going to have, that's a red box. If we look here, we can actually see both of these things in this prime factorization. So this 3, 2, 2 sort of thing, that's right here. 3 times 2 times 2, right? It's backwards, but it's there. And then we can also see that this 18, 3 times 3 times 2, is also there. And they overlap a little bit, right? But that's fine, because what we know is that this number, which turns out to be 36, right? 2 times 2 is 4, 4 times 3 is 12, 12 times 3 is 36. This number 36 we now know is divisible by both of these numbers, and we can demonstrate that. And I hope this is really going to seal this in our minds a little bit here. If we take 36 divided by 12, right, that is going to be equal to their prime factorizations divided by each other. So what is 36? 36 is 3 times 3 times, actually, I'm gonna write it a little bit differently. No, that'll work. 3 times 3 times 2 times 2. And our prime factorization of 12 is 2 times 2 times 3. I'm gonna write it as 3 times 2 times 2, because the order doesn't matter, right? Just for the sake of clarity, because you'll see in the next step. If we take 3 times, and then we put parentheses around this, 3 times 2 times 2, right? And then you'll notice that's exactly what we have down here. Since we have that 12 prime factorization contained within the prime factorization of the least common multiple, we know that these will divide out from each other, and we'll just be left with 3. And this is confusing because it is an algebra class. These that's a multiplication symbol, not an x, so just be aware of that. And so we just have that 3 left, and so 36 over 12, well, that's 3, right? So that's obviously divisible. Now, what if we take 36 divided by 18? Well, that's going to be a similar setup. So we're going to have 3 times 3 times 2 times 2, because it's the same number on the top. And then on the bottom, we're going to have 18, and the prime factorization for that right over here is 3 times 3 times 2. So we're going to put that here. And now we're going to do the same thing. We're just going to add parentheses. So, whoops, sorry, that's the wrong place to put parentheses. Oh, sorry, whoa, I wrote that wrong. That's a 3 times 3 times 2, right? Okay, so yeah, we're going to have 3 times 3 times 2 times 2, right? And these parentheses aren't doing anything mathematically. I'm just using those to show you the grouping and how we're able to sort of, how these are the same thing, right, on the top and on the bottom. So same thing here, obviously, these cancel out, and now we're left with the 2 instead of that 3. But you can see both of these numbers were divisible. Why? Because we made it that way, because we decided that we would have both of those prime factorizations that we have written up here in the red and blue, both of those are contained within the prime factorization of the least common multiple. In other words, the least common multiple is the number such that you can take out the prime factorization of either of the two numbers you started with from that number. So the basic process for finding the least common multiple, so I'll just write process for finding LCM, is we're going to start by doing the prime factorizations of the two numbers. So we're gonna, let's try, I don't know, 8 and 12. I guess I'm really liking 12 today, but so 12, what's the prime factorization for 12? That is, again, and we already have it up here, right? But we'll just do it again. 12 is the same as 4 times 3, which is the same as 2 times 2 times 3, right? So we do the prime factorization of that. Okay, the other number was 8. Let's do the prime factorization of 8. Well, 8 is 4 times 2, and that is the same thing as 2 times 2, 4 times 2. And so now that we have these, here's what you're going to look at. You're going to look at each number, each prime number that appears in these prime factorizations, and you're going to say, how many do I need minimum, right? So in this case, if we look at the 12, it has 2 2's, right? But the 8 has 3. So we know we're going to need at least 3 2's because 8 has 3 2's. And that actually, because 8 has the most number of 2's, that's the number we're going to go with. So we're gonna have 3 2's. So our LCM is going to have 3 2's. And then how many 3's do we need? Well, 8 doesn't have any 3's, but 12 has 1 3. So we're going to need 1 3. And now that's our LCM. Because you can see, if I again highlight these in this kind of a way, we can take the 8 out of it, right? The 8 is contained in there. And we also have this 12 contained in there. And so really, it's a very simple process. The idea sounds complicated and it's a little bit hard sometimes to wrap your mind around, but really what you're doing is you're building a number so that you can pull either one of these numbers out of it, right? So this bigger number, the LCM, you can pull a 12 out of it and you can pull an 8 out of it. And that's because it's containing both of their prime factorizations. If we wanted to take it a step further, we could actually even find the prime factorization of 3 numbers. And so let's say we wanted to do the prime factorization of 10. Oh, let's not do that in red. Okay, we want to do sorry, not the prime factorization, the least common multiple, I should say, of 10 and I'll just write them underneath each other. We have 10, let's do 8 again, and maybe a 6, right? So it's the exact same process. We're going to start by writing their prime factorizations. So 10 is 2 times 5. And it turns out 5 is also a prime, right? You can't divide it by 2, can't divide it by 3, can't divide it by 4. So it's a prime. It's only divisible by 5 and 1. So that is the prime factorization of 10, and I'm going to label that in blue right here, box that. Okay, 8, we already know that's 4 times 2, which is equal to 2 times 2 times 2. I'm going to label that in red. And with 6, 6 is equal to 2 times 3, and that's all you need for the prime factorization. We're going to label that in green. So now let's build our LCM. So we're going to go over here, LCM. So I generally like to start with the smallest number and then work my way up. So 2, what do we do with 2? How many 2's are we going to need minimum, right? So both the 10 and the 6, their prime factorizations have a single 2, right? These guys. And that's that would be enough if you're just doing these ones. But the 8 has 3 2's, right? 1, 2, 3. And so we're going to need 3 2's because we need to be able to take 8 out, right? We need enough 2's for 8 to be able to fit in there. So we're going to have 3 2's. Again, we're just having 3 2's because that's how many 8 has. Okay, now how many 3's do we need? Well, the only one that has a 3 is 6, and it only has 1 3. So we just need 1 3 in that LCM. And then finally, the 5. Again, 10 is the only one with the 5, and it only has 1, so we're just going to need 1 5. And that right there is the LCM. So if we wanted to sort of calculate this, you could say, okay, 5 times 2 is 10, and then 10, or here, 5 times 2 is 10, then 10 times 2 is 20, 20 times 2 is 40. Am I doing this right? Yes, okay, 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, and then 40 times 3 is 120, right? So that right there is our LCM. And if we wanted to check, we could say, okay, well, 120 divided by 10, that's the same as the 2 times the 2 times the 2 times the 3 times the 5 over the 2 times the 5. And we cancel the 2's, cancel the 5's, and we're just going to get 2 times 2 times 3, which is 4 times 3, which is 12. Right? If we did 8 over... 120 over 8, then that's going to give us the 2 times 2 times 2 times 3 times 5 divided by 2 times 2 times 2 for the 8. Those cancel. We just get 3 times 5, which is 15. And you could do the same thing with the 6. I'm not going to do that right now just for the sake of time, because we do have other things we need to move on to. So I hope that was helpful for the LCM. And if you're still confused, then you can ask me questions either in like the comment section of the YouTube video, or you could sign up for a tutoring session on the website. That'll be in the description on the video with me. Or you could just email me a question and I can try and respond to that. So hopefully there's a lot of ways that you could ask me about things and get help, because I try to, I mean, it's not really working very well, but I try to be fairly succinct in these videos. So so I'm not going super in depth into this stuff. because the next thing we talk about is even more important than the LCM. And actually, I do want to stop for a second and just note, I haven't told you how the LCM is actually useful yet. The reason it's useful is when you're trying to subtract fractions, right? So if you have like 2/3 that add or subtract, that, plus, I don't know, 3/2, you can use that LCM to figure out what your denominator has to be able to add those together. And we'll get to that when we talk about adding and subtracting fractions. That'll be, I think, 1.3 in the OpenStax textbook. So next we're going to be talking about a super important concept in algebra, which is variables. Maybe the most important concept in all of algebra and even math beyond. It's very important that we get this down. So a variable, it's kind of like a placeholder, and it represents a certain value, but we don't necessarily know what that is yet, and it can actually change depending on the situation. So that's probably really confusing if you don't already know what it is. So let's just give an example. So a lot of the time, your variable is going to be written as a letter, right? Rather than a number, we're going to use a letter. More often than not, you're going to see X used, but you can use A, B, C, all of the letters of the alphabet. It doesn't matter. So let's start with X, and X plus 20 minus 3X. This is what we're going to write here. And you'll notice we can put X in these places pretty much like any other number. You can add them, you can subtract them, you can multiply, divide, do exponents. Anything that you can do with a regular number, you can pretty much do with a variable. You just don't always get to combine them the same way. So this, we call this an expression. It doesn't have anything to do with the fact that there's variables. That's just the name for when we have a bunch of numbers combined like this. And so normally with some problem like this, you'd say like equals, and then you'd evaluate the expression. So let's say we had 3 plus 20 minus 3 times 2, right? Well, then that would give us a certain result, right? Well, we don't have that with the variables. Because, like, what does this equal? Well, we actually don't know, right? We don't know what that equals, because it doesn't equal anything yet, because we don't know what X is. What we can do is X can at any point, actually, we realize it has a value, right? So for example, X, let's say we say that X equals 3, right? That means that whenever we have an X, that is really just meaning 3. If we're given that, then now we can actually figure out what this thing equals, right? So if X equals 3, right? If X equals 3, then X plus 20 minus 3X, well, we can just take X, and everywhere where we see that, we can just replace it with a 3, right? So this is going to be a 3. That's a weird squiggly 3. We can have a 3 plus 20 minus 3 times X, which is 3. And so now we can actually evaluate this expression, right? That's the same as 3 plus 20 minus 9, and 20 minus 9 is going to be 11, and 11 plus 3 is 14. So the point is, X can have a value. It represents a value, but it works as kind of a placeholder when we don't have a value yet. And also, that value could change, right? Like, let's say now, okay, well, if X equals 2, right? Then now, X plus 20 minus 3X, it's not going to equal 14 anymore, right? Because, why? Because we put 2 in for X here. So 2 plus 20 minus 3 times 2, and that's going to be 2 plus 20 minus 6. 20 minus 6 is 14. 14 plus 2 is 16. So now it's not 14, it's actually 16. And that's just because x was a different value. And what's really powerful here, and you might think, okay, that's not very useful because now we just have something that we never know what it's equal to. Well, actually, it's really useful because it allows us to write things in a very general way. And what that allows us to do is we can say, for example, let's say we wanted to communicate the idea that a number squared means just means that number times itself, right? So how would we write that? Well, we could say, okay, well, 1 squared is equal to 1 times 1. And 2 squared is equal to 2 times 2. And, sorry, that's not 2 right there. There we go. 2 squared is 2 times 2. 3 squared is 3 times 3, ... Right? You could write that, and I think people generally get the idea. But it's still a little confusing, and it's definitely a lot to write. What would really be nice is if we could just say any number squared is going to be that number times itself. And with variables, we actually can, because we don't care what the number is right then, right? So we can actually just take all of that and sum it up in one statement saying x, any number, squared is going to equal x, that number, times, okay, and we'll use our now new stuff in algebra for multiplication. We use a dot for multiplication so that we don't get confused with x. It's going to equal that number times itself, right? This right here says everything we just put in here, but so much faster and more accurate, really. It tells us that any number whatsoever squared is going to equal x times x, right? It's going to equal that times itself. And so this is where variables can become very helpful. And there's a lot of ways you can use this. The real point you just need to carry away is that variables allow us to write very general statements that apply to many different numbers all at once. And you'll see it can help us identify things in equations, which we will also get to. That's going to be, I think that's actually a chapter 2 in OpenStax. We'll get to solving linear equations. So now that we do that, I just want to point out a couple of words here that we need to know, vocabulary, because, language of algebra is the title of this chapter. When we take an x like this and we stick it into the equation, like over here, and then we get what its actual value is, we call that evaluating the expression. And we'll kind of get into that a little bit more when we talk about expressions, which is actually right after this. The last thing I just want to cover is the idea of constants, okay? So you'll see if we go back, I'm just going to write it out again. Our equation was x plus 20 minus 3x, right? A constant is just a number. That's literally all it is. The reason we call it a constant is because it's not a variable. A variable could change, right? It could be a different thing every time. A constant is always going to stay the same, right? It's constant. So that's why we call these numbers, like 20 right here, is a constant. I'm just going to write that here. That is a constant. Same with the 3, also a constant. So literally it's just numbers, but we have a special name for them because we gave variables a special name and we wanted things to be fair. Okay, so now that we have variables and constants, we can get on to talking about expressions and equations. I promise there's not that much left after this. This video is already way longer than I expected it to be. But expressions and equations. An expression, it's very simple. All it is it's a number, a variable, or a combination of numbers and variables using operations. And so that's all abstract. Let's just give some examples of what operators are. So not operators, what expressions are. So here's expressions. I'm just going to write a bunch of things. They're all going to be expressions. 4x, 4 times x, 2 plus 3 plus 4, 5x minus 2. These are all expressions, and you'll notice it's just what the definition said. It's a number, okay? It could be a number, it could be a variable, or it could be a combination of numbers and variables, like this right here, right? All an expression is it's a statement of these combinations of numbers and variables that eventually can give us a value, right? And like I said before, I was talking about evaluating expressions. That's what these expressions are really useful for, because what they all have in common here, all these guys, if you have, if you know all the x's and everything, then they actually all turn out to give one value, right? They don't give the same value, but they all give a value. So this 4, well, its value, if we were to evaluate that expression, that would just be 4. That's like the simplest expression you can have. X is a little bit different because, again, it's a variable. It's still an expression, but it has a variable in it, which is x. And so we can't evaluate the expression until we know what x is. So let's just, for the sake of the rest of these examples, say that x is equal to 2. All right, we're just going to put that up in the corner here. If x is 2, then how do we evaluate x? Well, we just plug in 2 wherever we see x, which is just equal to 2, right? That's pretty boring. If we take the expression 4x, or 4 times x, if we evaluate that, that's going to give us 4 times what? We plug in 2 for x, and so that's going to be 8. 2 plus 3 plus 4, if we evaluate that, you see we have multiple values within the expression, but we can sort of combine them all into one value. That's evaluating the expression, because you're extracting the value from the expression. E-value, right? Evaluating. So 2 plus 3 is 5, 5 plus 4 is 9. And then finally, for sake of completeness, we'll do this one. 5 times x, we plug in 2, minus 2, that's going to be 10 minus 2, which is 8. And so that's all an expression is. It's a number, variable, group of numbers and variables, and you connect them with operators. So these operators are things like multiplication, division, adding, subtracting. All of those things are different operations we can do to combine different numbers. And we're going to talk about that a little bit more in a second, right after we mention equations. And so really all an equation is it's a way to compare two expressions. So let's just take two of these expressions. And at this point, this x equals 2, that's just going to be confusing from now on, so don't pay attention to that. That actually, let's put it back. We're just going to make it clear that is no longer true in the rest of the examples here. So if we move from expressions and we change it to equations, all the difference is that an equation is going to compare two different expressions, and it's going to do it in a very specific way. It's going to say that they're equal to each other. So if we have let's take the expression 2 plus 3 plus 4 that we had above, right? And we are going to say that's equal to 5x minus 2. Now, again, x is no longer 2, so you might say, okay, well, that one was 9 up there, and that one was 8. They can't be equal. We're now just assuming that they are equal, and x is no longer 2, right? So x is not 2 here. That means we don't have to worry about that being a thing. In fact, actually, let's just start with an example that's not going to have x's in it. That way we can really be sure of what we're doing. So 3 plus 2 is going to equal 6 minus 1, right? And so what an equation is it's going to tell us, okay, we have two different expressions. One is 3 plus 2, one is 6 minus 1 in this case. And we're saying that the value you get from evaluating those expressions is going to be equal. It's going to be the same thing for both of the expressions. So for 3 plus 2, if we evaluate that, that's 5. And that's equal to, if we evaluate 6 minus 1, that's going to also be 5, right? So they are equal, which is exactly what our equation told us. All an equation does is it says that the values that are going to come out of these expressions have to be equal. They are going to be equal no matter what, right? And so that includes if we have variables. So if we say that 2 plus 3 plus 4 is equal to 5x minus 2, right? We are saying that this is true, right? X is now going to be whatever it needs to be to make it equal, make this equal thing true, right? So if 2 plus 3 plus 4, well, 2 plus 3 is 5, 5 plus 4 is 9, right? We already did that. If 9 is going to equal 5x minus 2, x is going to have to be a certain value to make that true. Specifically, x is going to have to multiply with 5 in such a way that 5 times x is 11, so that when you subtract 2, you get that 9. Don't worry about that part too much. That's getting more into the equation solving, which you'll get into in the next few videos here. But I just wanted to put that, and it also turns out there are other ways, other than equations, that we can compare two expressions. So they might not be equal, in which case we'd say, we couldn't make an equation, because I can't say that 3 equals 2 and still be correct. That's just wrong, right? Instead, I could say something like 3 is greater than 2, right? That's what this little symbol means. That means it's greater than, right? The big side of that symbol is pointing to the bigger number, right? The open side. Or I could say that 2 is less than 3. So these different things, we call these inequalities. So these are inequalities. Why? Well, because they are not equal, right? We're just comparing two expressions and their values. They're not equal, but we can say things like, oh, it's bigger, right? Or it's smaller. And we also just have a couple of other ones. Less than or equal to is what that one means. We also have greater than or equal to. And those are really the main ones. We also just have one that simply says it's not equal to. That's what that means. So I could say 2 is not equal to 3. And that would be just fine too. So those are just different ways we can compare two expressions. So you can kind of see how these ideas build on each other. You have variables help you build expressions, right? Then you have equations use expressions and compare them to each other. And so now we can talk a little bit. I'm just going to go super quickly through operators. And these are just some common things we're going to do to combine numbers in algebra. You'll probably be super familiar with these already. You've probably been using them. But I'm just going to go back over them again. Operators in algebra. So an operator, all that an operator does is it combines two numbers, or two variables. Okay, so, I should say, really an operator performs an operation on one or more numbers or variables. So performs an operation. That's the gist of it. It's performing an operation, and it can be on just one number. It can be on two numbers. For most of them, it's going to be two numbers. So, for example, 2 plus 2 is 4, right? Well, the operator here is this plus right here, right? That's an operator. If we did the same thing with a subtraction, right? So 2 minus 2 equals 0. Now this minus here, that's an operator. What's the operation they're doing? it's addition for the plus and subtraction for the minus, right? If we did multiplication, this is very basic. Really the ones you're going to want to know super well are addition, subtraction, multiplication, division, and exponents. That's kind of the weird one, I guess. Multiplication, we have a bunch of different ways of writing it, and they all mean the same thing. So I'm just going to write them all out here. All of these mean the same thing for multiplication. So we have 4x, right? If you have a variable, you can just put the number right next to it. That means they're multiplied. Or you could say 4 times x, right? But see, that's kind of confusing because it's, the x, but that just means multiply 4 times x. Okay. Because that's confusing, we have this dot sort of idea here. So 4 times x with a dot. You could wrap them in parentheses and just put them right next to each other, 4 and times x. You could say 4 times just x in the parentheses, or you could have 4 in the parentheses and x outside. The idea is we have a bunch of different ways of writing multiplication. They all mean exactly the same thing. We also have a bunch of different ways of writing division, similar to multiplication, right? We could say 4 divided by x, right? That classic division symbol. We could say 4 over x. We could, like kind of in a horizontal fashion, we could say 4/x. That just means over x. We could be a little bit more helpful and say 4 over x like a fraction. Or we could also say this is a little bit more of an elementary school kind of way of doing it. 4 divided by x in this sort of box thing. All those things, they all mean the same thing. It's that, yeah. And then the last one is just exponentiation or an exponential operation. And all it is we use a superscript, right? So 2 to the third, right? We do this superscript guy up here. And that just means an exponential, which means that this is the same thing as 2 multiplied by itself 3 times. So 2 times 2 times 2, which we've actually seen quite a bit today. That's equal to 8. So that is how we do exponentials. And those are really all the operations you're going to need to know. I just needed to cover them for the sake of following the textbook. Finally, or almost finally, we're going to talk about order of operations. The reason is, let's say we have something like 4 times 2 plus 1. This is an expression, right? Like we just learned. And we want to evaluate it. Well, the question comes up, what do you do first? Should I say 4 times 2 first, or should I say 2 plus 1 first? And the answer is actually that we are supposed to do the multiplication first. But why is that? Because we have this convention that we call the order of operations. And what the order of operations is a specific way that people have defined how we're going to do this in the right order. So the way to memorize it, or the way that a lot of people memorize it, is this acronym PEMDAS, okay? And there's different sentences you could use to even remember that acronym. I know one is, please excuse my dear Aunt Sally. But I think PEMDAS, just the acronym itself, is fine. So what this says is parentheses come first, right? And that includes other grouping elements. So that's like, you could use parentheses, you could use brackets, you could use these curly braces things. All of those come first. Second, exponents, right? We just talked about exponents. That's like 2 to the third. Those get evaluated right after those parentheses. Then we have multiplication and division, right? It's a little bit confusing because these guys go on the same line because they're kind of in the same league with each other. And really, the order for these things is gonna end up just being left to right. And we'll get to that in a second. And then finally, after multiplication and division, we have addition and subtraction, right? Same thing with multiplication and division. They're in kind of the same league with each other. They don't get any specific preference. We just evaluate from left to right. So, for example, if now we can see, right, our 4 times 2 plus 1. Well, we're going to do the 4 times 2 first, so that's going to be 8 plus 1, and then we get a 9. Let's do one that's a little bit more complicated. This one, yes. 4 times 3 divided by 6 plus 2 times 2. Right, so what is that? That's kind of complicated, right? Well, 4 times 3 divided by 6, we know from our PEMDAS, multiplication and division come before addition and subtraction, right? But it's still kind of confusing because we said, okay, multiplication and division happen at the same time. Well, do we do 4 times 3 first, or do we do 3 divided by 6 first? And the answer is left to right. So we start with the leftmost one, which is 4 times 3, which is 12 divided by 6 plus 2 times 2. Then we're going to do the 12 divided by 6 part, right, which is 2, and then plus 2 times 2. And, right, we're just going left to right through this. And then that's going to be the same as 2 plus, and then 2 times 2 is 4. And then finally, we can do the addition and get 6 here. So you'll just have to follow this order of operations that we have. For example, if we had put parentheses right here, right, then that 3 divided by 6 would have happened first, and then everything else would be wrong, right? So we're not going to put parentheses there. Everything in parentheses happens first, then in exponents, multiplication, division, addition, and subtraction. So just remember PEMDAS. Okay. Combining like terms is the next section. This is, again, this video is kind of a hodgepodge of things, right? It's not super well connected. I try to connect it a little bit, but combining like terms, it's just helpful when we're evaluating expressions that have variables in them, mostly. So let's just go through this. So a term is a constant or a product of a constant and one or more variables. All that means is, from some examples, so it can be a constant, like 2, 4, or it can be a product of a constant and one or more variables, right? So 3x squared, 6y, see, because I'm using a different letter on you, or it can be 2 or more variables, right? So, one or more variables, so, it could be 2xy, right? That's really wild. It can also just be a variable in itself, so just x, right? It can be all these things. And when we have these in an equation, an expression rather, a lot of the times we want to simplify as much as we can, make it look a little neater, and ultimately that's going to bring us to combining like terms. So like terms are terms that we're allowed to combine just immediately, right? No matter whether we have a value for a variable or anything like that, we can just do it. So for example, 2 and 4 are like terms. Why? Well, because they don't have any variables, right? Constants are always like terms, just by themselves, right? A 2, a 4, a 6, a 5, anything like that. Those are all like terms. And other than constants, right, when we have terms that have variables in them, like 3x squared, 6y, things like that, then the concept of terms, like terms, is going to be based on whether or not the terms have the same variables to the same power, to the same exponent, right? So let's take 2x squared plus 5xy plus 6x squared minus 2xy and we're just really quickly going to combine all the like terms, right? So how do we know what is a like term, right? Well, it's any term that has the same variable to the same power. So when we're simplifying this expression, we're going to start with 2x squared here. Does it have any like terms? It does. It's this 6x squared over here. Why? Because 6x squared, the constants don't matter. It has the same variables, right? They only have x, both of them, and the x is raised to the second power on both of these terms, right? So if this were just 2x, then these would not be like terms. But because it's 6x squared, these are both like terms, we can combine them. So that's 8x squared. And so you can kind of think about it. Okay, I have 2x squareds, and I'm combining that with 6x squareds. So how many x squareds am I going to have now, right? I'm going to have 8. 6, 7, 8 from 6 plus 2 here. So the 6 plus 2 becomes 8, and the x squared just stays the same. Now let's move on to the 5xy here. So this guy, does he have any like terms? And the answer is again yes. He has the minus 2xy. Why are they like terms? Because they have the same variables, x and y, both of them, raised to the same power, 1, right? All of these variables are at the first power. So we can combine these. The 5 minus the 2 is the 3xy, right? Again, if I have 5 xy's and I subtract 2 xy's, how many xy's am I going to have left? 3. So that would be the simplified version of the expression from there. And so that's kind of the basis of combining like terms, is that in general, when you have an expression, you're going to want to take all those like terms that you can find and just put them together, combine them using these operations. And notice also, I had to take 5xy. I subtracted the 2xy because it's minus 2xy. I didn't add them. You're not always going to add them. Sometimes it's going to be subtraction, and sometimes it's going to be addition. It just depends. That's just a really important concept for the rest of algebra. You're probably familiar with it from Algebra 1, but I'm going over everything here. So, okay. And now finally, just a really quick overview of English phrase to algebraic expressions. I'm not going to do too much on this. Basically, the idea is sometimes we're going to have math written, rather than, 2 plus 2, they're going to tell us 2 plus 2 or something like that, right? Which that can happen in for different reasons in different places, like a word problem or something. And there's just a bunch of ways to say these things, and you just kind of need to get familiar with all these. So we have, if we wanted to say a plus b, right? See how I'm using those variables to make a very general statement, right? A plus b, you can say things like a plus b. You could say you could say the sum of a and b. You could say b more than a. B added to a, the total of a and b. There's all kinds of ways to say this. Same as subtraction. You're going to have things like, so a minus b, you could have a minus b in that sort of wording, right? You could say the difference between a and b. You could say a decreased by b, b less than a, b subtracted from a, things like that. Multiplication's a little bit easier. There's less things. So if we say a times b, well, okay, we obviously have a times b with those words, right? We could say the product of a and b. You could say, this one comes up a lot, so I'm gonna write it down. A of b, right? that one I feel like I see frequently and is kind of key word. If you see of, it could mean multiplication. And division, A divided by B, the quotient of A and B, ratio of A to B, B divided into A. All those things all mean the same thing. So hopefully this was really helpful. There was a lot covered today in this video. We covered prime factorization, calculating the LCM, right? We talked about expressions and equations. We talked about inequalities, operators, order of operations, and then we also discussed the English wording of things. These are just very foundational concepts for algebra. They're related. Some of them are more related than others, some less. This was a really long video. I'm very sorry for making it this long, but I hope that this was helpful, and I hope that you can do some exercises to get this all really solidified. If you are not feeling comfortable with it, if you have any questions, you can ask about the tutoring. I do tutoring sessions and you can sign up for those on the website that I will link in the description. You could email me, you could just put a comment or something. If I really want to help, so if you have any questions, please be sure to send those to me. And I hope this video was helpful. It was definitely really long. We covered probably way too much. Other videos, this first chapter of OpenStax is gonna kind of be a lot of review and stuff. Then we're gonna start getting into like solving equations and things like that, and it'll be a lot less to cover all in one video. This is just a bunch of hodgepodge things. In fact, I might split this up into multiple videos. I don't know. But yeah, I just hope this was helpful, and yeah, I'll see you in the next video.